working on large-scale event processing systems. Before that, I worked on reactive extensions. I'm one of the original developers of RX.net. And so what I'm building right now is a highly scalable distributed variant of that platform. And so throughout the years, in building this system, which we call Reactor, it actually powers a whole bunch of things like Cortana on Windows 10, for example. In building that system, of course, we had some challenges with scale and performance to overcome. And so this is kind of a talk with tales from the trenches of things that went bad and what we learned in doing all of that kind of stuff. Just to give you a sense of the scale here, this thing is running about up to 1 billion queries that are standing in memory all the time across a couple of hundreds to thousands of machines. So in some sense, it's a relatively small service in terms of the physical hardware that we have, but in terms of the volume of data processing we do, like thousands of events against billions of queries, it's actually quite big. It's all built on top of Service Fabric and .NET, as well as .NET Core most recently. So we are actually a pretty big consumer of the common language runtime and C# and all that kind of stuff, especially things that have to do with system reflection emit and all sorts of runtime compilation of user queries. So it's pretty much a big compiler in the cloud with a huge optimizer on top of it, to do a whole bunch of interesting things. Now, it's totally possible that the stuff you guys built is quite different, but what I'll be talking about is general advice on how to analyze certain performance issues, the kind of pitfalls to actually watch out for. Now, before getting started, I just want to talk very briefly about this kind of performance engineering strategy that when we're building a system like this is actually good to sort of have in check in your team. So one of the things we do an awful lot of course, in large-scale services like Bing is having a lot of instrumentation and a lot of counters so we can know where the performance goes in a production system. There's nothing more valuable than knowing where the latencies go in a very long request pipeline that maybe stretches over hundreds of mini requests and 100 components that sort of happen during the lifetime of a single request. So you want to have this good set of measurements, and there's a lot of ways of doing that. I'm not going to talk about using things like App Insights in Azure or some other facilities. Have something that your system isn't a black box and you don't know what the heck is going on, of course. Second thing is the performance culture. If you know that performance is going to be critical for your system, then of course it's good that everyone on the team has solid understanding of the performance goals and you define some metrics that you will go by. In our case, it's like the number of queries that we can host in a single machine, for example, is a key metric. Like if we regress that by 5%, that means like purchasing a couple of, in some cases, hundreds of extra machines. Like, that's a lot of investment, to sort of, regress performance. So you don't want to be doing that. So some general purpose advice over here, all common sense in some way. Now, second thing, know your tools. The tools that I tend to use are the ones I'm going to list here, but there are many other tools that are useful. For example, JetBrains has excellent tools to do memory analysis, for example. The ones that I sort of stick with the most right now, at development time, the stuff that we have in Visual Studio, especially Visual Studio 2017, we have great memory diagnostics capabilities over there. So you can actually use everything that's built into the product over there. In production systems, we tend to not have Visual Studio installed on every single machine in the cloud, so we use some other tools there. One thing that we kind of always tend to fall back to, and it's always good to understand a little bit of that, is WinDbg and SOS, which is a native debugger extension. Even if it's just, a service is crashing, you have a dump file. The dump file is like our machines. Some of them have 128 GB of RAM. If you have a dump file of 100 GB, you're not going to copy it to your Surface laptop to sort of look at it in Starbucks or your favorite coffee shop. You will remote desktop to that machine and use the tool that's available on the machine. So in a lot of cases, we just open up WinDbg, take a look at the dump file, and see like what the heck was going on in this particular system. Purview, how many of you have used Purview or heard of Purview? Yeah. So Purview is a tool built by the CLR team. I'll show a couple of things later about it. It's a great tool, very lightweight, X-copyable. It's just a couple of megabytes. You can just copy it to the machine and take a look at, in real time at, the stack traces and all that kind of stuff where, the CPU cycles are spent, where the memory allocations come from. A great indispensable tool at this point. And then finally, CLRMD. How many have heard about CLRMD? Less, yeah. CLRMD is actually a managed code wrapper on top of all the APIs deep inside the common language runtime that enable you to look at the runtime as well as on dump files at the memory structures of the CLR. So you can actually build your own debugging tool, just like SOS allows you to take a look at everything on the heap, everything on the stack, what the thread pool is up to. This tool actually builds on top of that and provides a managed API experience. And in fact, for a lot of analysis things that I have to do, I always use CLRMD. Because when you look at SOS, well, you can say, like, what's going on here in terms of, why is this object still alive? But then you may have a very domain-specific problem where you see, oh, we have like a chain of 100 tasks that are sort of like linked together, and we want to know like who's keeping that alive. At that point, it makes a lot of sense to build a custom tool that says, like, show me all the continuation chains of tasks, for example. And SOS doesn't know about task of T. It doesn't know the internal structure. You can sort of go one task at a time and chase pointers. But with CLRMD, you can actually write a link query that says, like, from all the objects on the heap which are of type task, find me the continuation to that task and sort of stitch it together. So you can start building link queries on top of debugging APIs, if you will. Super powerful little thing. So I may show you a couple of examples of that towards the end of the talk. I have a couple of slides here which I'm just going to blast through really quick. The goal is to make those slides available. I think they're already available from a previous conference I spoke at, but this is kind of just a tutorial on how to get started with each of those tools. You can find plenty of stuff online, like how to start with WinDbg and SOS, pretty easy. How to start with Purview, that's a UI tool, so even easier. I'll show you an example of that one later, but this is kind of a little picture on how that sort of looks. I'll give you an example in a bit. CLRMD is a NuGet package, so just create a new console application, import CLRMD. The main thing with those kind of libraries is, if you haven't used them, like where to start. So all this slide is telling you, look for a class called dataTarget and start partying. Like you can say dataTarget attached to process. And from there on, you can start inspecting all the memory structures in that target process. If you have a dump file, you can do attach, to a crash dump, load crash dump over there. So just some little tidbits here. Okay, now let's get started. So what I have next is a menu of maybe 20 cases of things that we ran into. And so those will actually always have some grand lesson on how to make sure that your service is performant and the kind of mistakes we ran into in the past. So the first case I want to talk about is what I call the case of the trace. What happened here is the following thing. When we built Reactor about 4 to 5 years ago, we started on this effort. The state-of-the-art tracing system in .NET was TraceSource. Thou shalt use TraceSource because that's the best thing since sliced bread and hot water. And so we actually subscribed to that notion. We started using TraceSource. And TraceSource has this mechanism where you can just talk to the trace source and just log things, and then it can go to multiple trace listeners. And so as we got more convinced that this was actually working quite well, we added more trace listeners. And one day the system kind of plummeted, the QPS went almost to 0 at some point in time. And so the thing we ran into is that this deceptively simple API that just allows you to log some strings has a lot of cost underneath it in case you use trace listeners which are not thread safe. And this is actually the code deep inside TraceSource that was responsible for a pretty big service issue that particular day. So by adding a new trace listener, you can influence this flag called useGlobalLock. And when you see the word global and lock combined in one sentence, you sort of have to start thinking something may be afloat here. And so we actually started entering this path. And so all of the tracing was now happening, including going over all the listeners, because there was one listener that said, I'm not thread safe. From that point on, like all the access to all those listeners, which are I/O bound, were of course being synchronized in the process. So like, if you have a machine with 64 cores, which we like to use for massive parallel processing, and you throw in a global lock, you could equally well just run Windows 3.1. So, nothing much happened there. Now, to make matters even worse, the formatting happens on a per listener basis. So every listener will do string formatting under that lock. And string formatting is not exactly the most cheap thing to do. So the things to be aware of here is, there are sometimes deceptively simple APIs where with a little bit of config, you can sort of cause a major avalanche in performance. And I'm always very aware when I see APIs that take in, a params array of type object array. You see boxing coming around the corner, all those kind of things, which can cause major performance issues. So the short-term resolution there was, of course, to just, disable that trace listener, which was kind of throwing a wrench in the whole thing. But more long-term, and I'll talk about it in a moment, we actually moved completely away to EventSource. How many know EventSource? Yeah. So EventSource is a much more interesting system to do tracing. It's based on ETW, which also all of Windows and the .NET framework is using. So very robust system, and I'll show you a couple of examples of that in a moment. Now, to make matters worse, we were also faced with huge exceptions. So exceptions are an interesting thing because they should be exceptional, and if they happen occasionally, you want to put them in logs so you can actually find like what's happening in my system. So you definitely want to log exceptions. But the toString method on an exception is, of course, a virtual. And if it's an arbitrary exception, you don't know what that virtual is going to do. For all you know, the toString is overridden to just do thread.sleep infinite, right? Most of them don't do that. But the aggregate exception, for example, is a notorious source of a lot of allocations. If you take a look at the toString of aggregate exception, it's actually a loop that's kind of aggregating all the inner exceptions by doing string.format one at a time. So you can sort of see like, this is more like, a punishment room for the GC. Like try to print this thing and a lot of stuff is going to happen. So of course we were logging those suckers at some point, and the fact that we have millions of those queries running per second, what happened is that when a service fabric replica becomes primary, we load a whole engine of millions of standing queries that will happily be evaluated. When that replica becomes secondary, we unload it from memory because something else has become primary. It's been primary elsewhere. So we unload that thing, and to stop those computations, we sort of inject an exception into them to bail out. So we had 1 million of those exceptions, all getting a bailout exception, and of course they were all being aggregated higher up in the unload async, throwing an aggregate exception saying computation 17 has been unloaded, 18 has been unloaded, 1 million of those guys. And so we ended up with a single log file of 30 MB. That's the threshold for a single log file that we upload into a log store. A single log file containing about only half of the single toString output of a single exception being printed. And so that was also happening and being passed into that params array on trace source. So all of that stuff was happening under that lock. So at that point, you have like tens of replicas running. One gets unloaded, wants to log its single exception, and all the other ones are just plain stalled, not doing anything, because they just want to write, it's sunny weather today, like something very small, into the log file, but they're all bouncing on that global lock. So, knowing that there are some things underneath you is sometimes a good thing. And so, for example, in our system, we don't allow, calling toString on system exception anymore. We sort of have a repository of exceptions, how we want to print them, because in a lot of cases, like printing something like, target invocation exception, well, that also, has an inner exception, and you want to print the inner exception. So, calling those virtual things like toString, the return type already says, I promise you I'm going to allocate a lot of stuff. And I'm not going to tell you how I'm going to do it. So on top of that, it's even worse. So you may want to sort of look at those things a little bit as well if you have a high density system. Now, how did we switch to EventSource? The essence of EventSource is that you basically get rid of this performance crime of making everything into a string. I kind of compare EventSource to PowerShell. right? Like, if you take a look at classic, scripting languages and, Bash and CMD and all those kind of things, they're just passing strings along and you need to parse them at every single place, right? Like you need to grab and set and awk and all that kind of stuff, at every single stage. Instead, if you can pass objects and rich structures around, you end up not converting them to strings. You never need to parse them again. And you can actually do structured queries on top of them. And so EventSource is based on ETW, event tracing for Windows, which is a very low-level API. And so by using this EventSource class inside .NET, you can actually piggyback on that infrastructure. In fact, tools like Purview are purely listeners to ETW events. So as soon as you're in ETW, you can actually start seeing your events being ordered in time amongst a whole bunch of other events that are happening. For example, the .NET Framework will raise an ETW event saying, oh, I'm acquiring all the logs in a concurrent dictionary for some reason, which likely can be a performance issue. But if you don't know where that's happening in the context of your application, it's kind of useless. But then if you also have a lot of ETW, you can sort of see what caused this thing to happen. So we actually use a lot of ETW nowadays. And one thing I would recommend you to take a look at is link to traces. This actually allows you to use reactive extensions to write queries in real time over those ETW events. So you can actually do aggregations in real time on top of what comes out of ETW. Now, how do you do this? It's pretty simple. You just inherit from a class called EventSource somewhere in the system diagnostics namespace. And then you just start writing some methods, and you call base class methods called writeEvent. Now, you can also do it more sophisticated with a whole bunch of custom attributes on top of these things. But this is kind of the basic way that you would declare an event source. And then instead of doing something like traceSource.writeLine and then some format string and yada, 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 you will simply call this method. So you will do mySource.log.requestStart and mySource.log.requestStop. Now, there is actually a reason that I have this start and stop pair here. Because if you start using start and stop in combination with EventSource, you actually get to some new feature in .NET 4.6, which is called correlation and causation. So what you see here, this is a screenshot of Purview. This is actually a piece of code that has been instrumented with request start and request stop. And you can now see the duration of all those requests as well. Like you no longer have your code littered with stopwatches everywhere, that you do stopwatch.start, stopwatch.stop, and see like what's the elapsed time here. You just log the start and stop events, and then you derive the time it took from that. And so that's how we feed it into our telemetry systems and metric systems, as opposed to like asking people, just allocate a bag of stopwatches and just start timing every single thing yourself. Now, on top of that, the beauty of this thing is that you also get nesting. So that's the new feature in .NET 4.6, is that if there are starts and stops happening as part of the same logical operation, which actually spans asynchronous calls as well, so if you do an async and await, you will not lose your causality tracing anymore. You will actually see this kind of request tree. So you see that there is an activity here called loop, which then spawned a fork join, which then spawned a request, and so on and so forth. So you can now sort of trace that whole request and see all the deltas in time between any consecutive starts, between starts and stops. So you can have the whole timeline of the whole request, sitting right over here. And so I'll just give you a very small example of that, just to convince you it's pretty easy to do. Here's an event source. Let me just make it slightly bigger over here so people in the back can see it. It's the most minimalistic demo I could actually do here. But you see, I'm using a lot of async and await over here just to convince you that you can be jumping threads all over the place on the thread pool and what have you. This infrastructure will actually keep track of the causality between all those things that I'm doing here. But so a request will actually, of course, in reality, you would take in the URI over here. But I do a request start and request stop, and those will be correlated together. And then deep inside of this, I'm doing an I/O, which, for example, does load something from disk, and then I'm just mimicking loading things from disk. But if in here I would be doing file I/O, and the file I/O subsystem in Windows is also using ETW with starts and stops and sends and receives, you will see all of that stuff being nested there. So you can actually see the Windows ETW events for the file system being sandwiched in between your ETW events. So you can get a perfect, causality chain across all sorts of parts of the stack, including .NET Framework, CLR, the Windows operating system, and so forth. So I'll just give a quick demo on how to run this thing. I have an EventSource demo.bat here. Let me actually show you what this thing does. This thing just starts Purview with a couple of parameters. The only interesting parameter it adds over here is Microsoft Demos Activities, which is on my event source. That's the logical identifier of my event source. In reality, you will have your own name over here, of course. And I'm starting it to collect traces. And so as I start this thing, you'll actually see my application run, and Purview will be tracing. So my application is running in the background over here. And now it's actually, collecting a trace, and I'll just do stop collection over here after a couple of seconds, because it's just a while loop that's just, creating requests. And so what Purview is doing right now is it's actually taking that ETL file, Event Tracing for Windows, ETW file, and it's actually analyzing it right now, and we'll actually start seeing on the left the CPU traces of, everything that happened in my application during that time. And so here we go. It actually finished. There's a zip file here, which contains the ETL file. And so here you go. You have now CPU stacks and all that kind of stuff. But one thing I can actually go to over here is any stacks with start-stop activities. And this thing will actually show me those start and stop events that I have. Now, ETW is system-wide, so you see all the other stuff over here as well. And I will have to find my EventSource demo. That's this process. So I can also use this to analyze the performance of Visual Studio or any managed process, of course. And you see I'm completely surrounded by even kernel events here, context switching events and all that kind of stuff. But you see over here my requests start, and you see all the individual requests over here. And if I open one of these, let me go to the call tree, I can actually just drill down into all individual requests over here, and I see I have a request over here which was doing a perform IO, which had a start and a stop event and those kind of things. So you can start drilling down into the causality of what caused what, and you can sort of start analyzing where the time actually went. Okay, and that's actually pretty interesting if you have components that sort of come together in a big service. You just ask everyone on the boundaries of the component to do start-stop kind of, tracing. And at that point, you can sort of see, which component was responsible for most of the latency in the system, for example. Now, another example or another case that we ran into is the case of the stuck finalizer. Interesting performance crime as well. So everyone knows what the finalizer does. It's the thing in .NET that when an object is ready to be garbage collected, but it still has native resources underneath it, then the GC will give it a second run, to sort of run the finalizer, which can close things like file system handles and those kind of things. Now, what we actually ended up with is, at some point in time, we saw the working set on all the machines steadily growing. And so that's a disaster sort of coming up, so we had to take a look what was going on over there. And also the I/O was becoming incredibly sluggish. Latencies to open sockets were sort of increasing. All sorts of bad things were starting to happen. And so one of the first things I tend to do when analyzing such a performance issue is to look at the finalizer queue in WinDbg and SOS. So I had a dump file of one of those machines being in a deep crisis, look at the finalized queue and seeing over there there are 82,000 objects ready for finalization, and they're not being cleaned up. So either the garbage collector is currently in Hawaii on the beach and not doing anything, but it tends to be a pretty hard worker, so the GC was there. So we actually took a look at the finalizable objects, and there we had our answer why I/O was actually becoming very sluggish. We had 627 sockets which were finalizable, holding onto native resources, but never got their native resources cleaned up. We had 4,300 thread objects that were still in memory, even though the threads were already dead, no longer in use, but they were still taking up 1 megabyte of stack space, all of them. So like the working set is going away there too. And we are actually doing a lot of stuff with system reflection emit, as you can see, and conditional weak tables to sort of like have weak references to objects that we don't want to stick around for a long time. Very interesting data type. If you're not familiar, you should take a look at conditional weak table. But if that thing doesn't get finalized, that means that there's nothing weak about the weak references anymore. Like everything is as strong as it ever has been. So massive memory leak. So what we found is then that looking at thread number 2, which is where the finalizer sits on this machine, we actually found that there was actually a lock happening, just waiting for some native resource on the finalizer thread. And so the finalizer thread was just simply stuck, deadlocked or locked in some way for a very long point in time. In fact, trying to do something with socket APIs in a library called CLRMD, which we happened to use at that point in time. In fact, we had PDBs for it, so we also found, the name of the developer that actually caused this problem to happen was Johnny. We don't know who Johnny is because it's an open source library from somebody else. But yeah, so this didn't work out. So in this case, we had to do something, to look at, the bugs in CLRMD and actually try to get around this. But beware of native resources. In this case, we were actually able to solve it by simply putting a using statement around some resource so that it doesn't end up on the finalizer to clean it up over there. The result of that was, of course, that it started locking, in the dispose call at some point. So like we had managed threads being blocked instead, but not the finalizer queue. So it was already a little bit better because the finalizer queue is a precious thing. But so ultimately we moved off this particular library. But anything to do with the finalizer, you want to be extremely careful about if something happens over there. Now, once we solved that, a couple of months later, we saw something similar, and that DLL was already gone, so we were kind of baffled, and yeah, it can repeat itself for a different reason, of course. So we ran into this a couple of months after the previous one. In this case, for some totally different thing. What we have here is something called Autopilot, which is the infrastructure that Bing runs on. It's like, something very similar to Azure, but much, much older, goes all the way back from, to the 90s. So that thing has some client that can be used to sort of send telemetry to dashboards, to warn people that something is going bad. And so we actually hooked up an event handler to the unobserved task exception on the task scheduler to actually send information about exceptions we didn't handle up into the cloud. Now, what's happening is that this task scheduler unobserved task exception is actually running on the finalizer. It's when the task that had seen an exception, which was not observed by the application, gets finalized, which we know that nobody can see it anymore. At that point in time, this event handler is raised on the finalizer thread to tell you, here's an exception that you haven't observed. So on the finalizer thread now, we are actually talking to an API which encapsulates some HTTP client in a synchronous manner. So in other words, like the finalizer is now waiting for those exceptions to go out. Now, the beautiful thing that happened here is that because of that, the thing that caused this was some unobserved exception on some socket API. This caused pressure on the finalizer, causing the sockets to be depleted, causing us to have more exceptions, causing us to deplete even more sockets. So this was just a spiraling effect for the system going completely down. So the answer to this is, of course, well, make sure that A, you know where this code is going to run. So in this case, we're no longer using this DM client in that particular spot. The second thing is observe your exceptions. And so it's a pretty important thing to do is to actually make sure that you're not lazy about like handling exceptions for async APIs. And there's one single reason that a default a default in the CLR has actually been changed, namely this thing. Starting with async and await being introduced, the default was changed for the behavior on unobserved task exceptions. Unobserved task exceptions will no longer terminate the process because in that case, people would not be able to use async and await in combination with UI applications where you have a lot of async void. And async void means nobody can see the exceptions coming out of it because you just throw them in the air. So this default has actually changed, but for server applications, it's not the best change in the world, I have to say. So we reverted that thing, of course, in debug builds. In a service, you also want to be careful not to just, take down your service because some developer forgot something. Like, the defaults are a little bit different in some cases. But so in the debug builds, we actually have this behavior set to a very pessimistic mode again. So like, we'll take down the whole service in our pre-production environment in case somebody forgets to handle an exception. So that's something you can do to deal with that. But be aware that there's actually many patterns in the BCL that don't exactly stimulate or make it easy to actually observe all exceptions. Here's a good one, which we actually ran into quite a couple of times. Quite an idiomatic way of canceling something if it takes longer than a second. The task.whenAny pattern with some operation and then a task.delay. And so then you just look at the outcome of that to decide whether or not the first thing was hit or the second thing, whether it was the timeout or the operation completing. Now in that case, if the task.delay actually wins, then that foo async is still going on at some point, and like nobody may be listening to that task anymore. Nobody may have attached a continuation there. So you may want to do something, even if the timer wins, to actually observe the exception, potentially log it in a way that you're not just doing toString. Remember the first case. But you may want to do something like this, a little bit more plumbing to make this work, and to have this kind of a delay. Now, on top of that, in a lot of cases, this foo async can also be canceled. So I've seen a lot of code where people use this pattern because MSDN says so. So you use this pattern, but you forget that you can actually cancel an operation that's timing out. So in this case, the foo async even took in a cancellation token. So I can actually cancel that in case my timeout wins. I can cancel the foo async to try to sort of undo it. So a little bit more code in these kind of cases actually does make a lot of sense. Okay, good. Now, continuing on the task.delay, timers. Timers are another source of beautiful expense that's everywhere, okay? Like, as soon as you have timers sitting underneath you and you don't know how many there are, you're up for like some roller coaster ride at some point in time. So, the timers in .NET have been improved a lot over the years, actually, but if you have a lot of them, you will still want to know that something is going on deep inside the common language runtime to help you being woken up because some timer is expiring. So there are actually 3 methods that at some point using Purview showed up as being the high hitters for CPU usage, okay? 3 things: the fire of a timer, the change for a timer, and the closing of a timer. Those 3 things showed up roughly 20, 30, 20% or something. Like most of the CPU was going to those 3 methods actually. And so what's actually happening deep inside the timer class is that there is actually a global lock to manage the timer queue. And the stuff that's happening under that global lock is not super expensive. It's just updating a couple of pointers. But if you're actually doing a shitload of those timers, you end up in interesting situations. Now, where do those timers come from? A good example is task.delay. So like if you have something that you're trying to time out and you have thousands of requests per second, and for all of these you want to time them out after 100 milliseconds or something, yeah, 1,000 requests per second giving birth to 1,000 timers that all need to be started and all need to be stopped. At that point, there starts to be some contention on this timer queue, okay? So, in fact, if you now go to the reference source or you go to GitHub and actually take a look at the source code for timers, you see that there is some interesting stuff over here. One thing in the perf assumptions comment in the code is, we assume that timers rarely actually do fire. Okay? It also says over here that it's very fast for insert and deletes, but there may be linear traversal when firing timers. So like, we also assume that there's relatively few of those guys. So there's a whole bunch of notes here detailing like, the sweet spot in the design that was chosen to be, the sweet spot at the time of building the timer code. Now, what's happening with this timer, or this task.delay, is that a lot of people in this previous pattern that I showed just a moment ago were actually doing task.delays, and then the delay is actually winning, so the operation is timing out, which means that timers that are just there for, timing out something, they're also expiring, and you never cancel them, even if the operation itself wins the race between itself and the timer. So like for everything that you're timing out in the system, 1,000 requests per second, all of them a timeout of 30 seconds. 30 seconds later is the hell for the timer queue lock, because all of those timers still expire and we didn't bother to cancel them, right? So like if you do this idiomatic pattern where you can cancel an operation because of a timeout and you can cancel a timer because of an operation succeeding, it's better that you double link them, that you also cancel the timer if the operation succeeds, because otherwise 30 seconds later you're paying the price for all of those timeouts starting to fire as well. So this task.whenAny is a good pattern, but don't make it a shallow pattern where you just slap that in and then sort of hope that everything will be good, okay? So observe the exceptions, try to cancel things which are cancelable, and of course you can abstract this whole thing into a little helper method if you like to do so, okay? Another interesting case is acquiring all locks. That also happened one day. You can actually see the code name of a project that we had in here. So just squint and pretend you never saw that code name. But what was happening here was actually using Rx, the reactive extensions. But so what's happening here is that somebody wrote a query, and inside that query they were using a concurrent dictionary. Because concurrent dictionary as well, it's concurrent, right? So it ought to be a good thing. I don't have to worry about locks, all that kind of stuff. And that's good, but there are certain properties on even data structures like concurrent dictionary that acquire all the locks. What's happening with concurrent dictionary is that there's a lock per bucket effectively, or like, well, not exactly per bucket, but there's fine-grained locks. So if some people are touching the dictionary for key A and some other people for B, they may never see each other, acquiring the same lock. But there are certain operations, if you think about it, well, something like count, it better freezes all of the buckets in order to get a consistent count property. Because if it doesn't do that, well, you may end up with a negative count or something, or like something weird. So something as simple as, like, for every event that was flowing, just checking whether the dictionary is not empty by doing count is larger than 0, was basically making the concurrent dictionary into a non-concurrent dictionary, which is even way more expensive than a regular dictionary with a single lock on top of it, because now we need to acquire locks for every single bucket in the dictionary. And of course, this dictionary was more often than not empty, so this check was not even worth it. So you end up in this kind of interesting situation where 31% of CPU that day was actually spent in the count property. Now you'll actually wonder, like, it's a lock. How can a lock spend CPU? Doesn't the lock just put the thread asleep and it will be woken up when the lock is actually satisfied? Well, the answer to that is locks inside the .NET framework have a little bit of spinning inside of them. Like, we do a little bit of spinning until the next yield point, such that in case we can acquire the lock before the CPU is going to be swapped out anyway, or like the thread is going to be swapped out, we can sort of hope for the sunny day scenario. In this case, the day was never sunny. It's Seattle after all, it's always rainy. So we ended up like, just spinning CPU cycles all the time to acquire a lock that would not be acquired within the thread quantum anyway. Another day, all the I/O stopped, which is not good for a web service. Maybe good for like, something that computes prime numbers or something. But in this case, like, all the I/O stopped one day. Another beautiful crisis, of course. Another thing that you may want to look at periodically if you're sort of tuning your applications and looking at applications in production, finalize queue is one thing. If that thing is unhealthy, you can forget all about it. Like, it's going to be the end of your career. Maybe not that bad. But the thread pool is another source of like precious resources. If your thread pool is empty, not much is going to happen anymore. So here's a good example. One day the thread pool, the completion port threads were actually 1 free. Now, what's the completion port threads for? When an asynchronous I/O is actually finished, using overlapped I/O APIs and those kind of things, a thread from the I/O completion port pool thread is actually going to be woken up to serve the continuation of the I/O. So in this case, nothing happened anymore, or nothing could happen. We couldn't serve any I/Os being completed anymore. That includes taking in incoming requests, sending outgoing I/O requests, hitting the file system. None of that can work anymore. Okay, so what happened here is the following thing. Again, beautiful stuff. You can already see at the bottom, I won't repeat it anymore. Another place where we were tracing exceptions. In this case, we were not doing it. It was WCF doing it. We had a WCF setting enabled in the production system that says, like, send detailed stack trace information to the caller when something goes bad for debugging purposes. Very expensive thing, because when an exception happens, it needs to do a stack walk, try to read symbols, all sorts of things need to happen to get detailed diagnostic information. And if this thing gets into a production system and things start to go bad, you can start seeing things going bad really fast because, well, one of those guys being served and trying to send the exception back to the caller may actually cause, some thread to be blocked for a certain amount of time. The second request comes in, is also starting to time out, cause an exception. You can see this kind of snowball effect happening again. So beware of your settings. Again, this thing is a single true, false Boolean flag inside a config file that causes major kind of things. So take a good look at things that are explicitly described in MSDN as use this for debugging only. Like, that flag says use this for debugging only. So don't ship that into the production system. Like, it's not like it's a liability or something. It's not in the small print, it's even in the big print. So, be careful of that. Now, what's happening here is you see on stack traces, that's something you may want to do periodically as well. We actually have a system that periodically takes a purview trace and stores it and then analyzes it offline. You can actually do that using CLRMD. Just let purview, take some traces and so on and then analyze them later. But one of the things to look out for is mon contention, which means monitor as in system.threading.monitor contention. That's actually, there's ETW events around it as well, which feed this contention counter inside the Windows performance counters. But over here, if you see a stack trace containing the word contention, then, well, things are quite contentious, obviously. And so what's happening inside this contention thing is the spin weighting stuff that I described just a moment ago. So even though all those cases in this presentation seem to be separate, they sort of all have a boundary condition. The previous thing was about spinning. Here's the explanation on how this spinning actually happens. So you can actually find that source code on GitHub as well if you want to see how the spin weight works. But here it is. Deep inside over here, you see try spinning and yielding before eventually blocking. There's an arbitrary number in here. Lots of software has arbitrary numbers. So in this case, there will be 10 repetitions of spinning before we actually put the thread asleep. And so that's what's going on over here in the contention code path. And so again, because we were doing something expensive, namely tracing exceptions, which requires acquiring locks to read resource tables to format the exception message in the proper language of the system, like all that kind of expensive stuff that we didn't need in the production system, we caused a whole bunch of lock contention, causing more timeouts in the system and so on. So you see those things sort of like shooting yourselves in the foot really, really quickly in that kind of case. So be aware of debug-only facilities. Don't have debug-only facilities in a production system, okay? That was actually a misconfig kind of thing. Using singletons. Another beautiful source of things. May not apply. Well, actually, this one will apply, but I have another one that may be a little bit more specific to our workload. But this one is a pretty easy one, just pointing this one out. Things like params arrays, for example, those are allocators. Starting with C#6, the C# compiler will actually emit more efficient code when you call something with a params array and you don't specify any arguments that go into the params array. It will actually emit code using array.empty of t, which is a singleton instance of an empty array, okay? So if you at some point are inclined to do like new empty array somewhere, you may want to know that there are singleton types available. So for example, there is this thing called type.empty types, which has been there since .NET 1.0. There is array.empty of t for an empty array, singleton, and there's task.completed task as opposed to doing return task from result 0 everywhere. You need to return a completed task. So those singletons are really useful because they sort of reduce background noise. Now, if you're at the point of reducing this kind of background noise, likely you've already graduated in the school of performance optimization. But those things, if they're everywhere, they can start showing up. Like I've had cases of the core event processing engine where the CPU sample showed like allocations of arrays, but this thing should not be allocating anything. It was just actually calling some member with a params array before C# 6.0. Like, and it was just allocating empty arrays all over the place. And of course, if you spend 5% of time in GC, may not be a big deal, but again, 5% of processing billions of events means like not processing stuff while the GC is happening. So if you want to go for low-hanging fruits, there's a lot of those small little things that you may just not be aware of existing, like task completed task, for example. Okay. Singletons, that's the other one I was talking about that may not be that relevant, but this is something you should be aware of. Beware of putting like static singletons inside open generic types, because you will have an instance of that singleton for every closed instantiation of the type. So in this case, there will be a foo instance for bar of int, bar of double, bar of string, bar of datetime, like because it's inside a generic type. And so it's often too easy to sort of forget the context where you are. Like, let me put a static read-only field here with a shared instance, but then it's sitting in an open generic. And in our service, well, there we have a lot of T's because every event schema is a unique T. And so we're doing billions of events, that we're processing, or like thousands of events per second that we're processing with lots of different, schemas. So if we end up having an expensive singleton, like let me cache, the first billion prime numbers here because I will need them all the time for something, and you do it in a generic type, well, then you will have a billion prime numbers per type, right, at some point, and you don't want to do that as well. So be aware of this little caveat. Another one, subtle sources of boxing. Now we're sort of at the, little things that sort of show up as background radiation. The previous things were, oh my God, the whole system came to a grinding halt, like what's going on here. This is, when you're over that hump, or ideally you're never there, and you start looking at the system and you come to the conclusion, oh, there's a lot of background stuff happening here, you may want to look for those kind of things. Here's a good example. Calling something like get hashcode and dot equals on an enum causes boxing. Like, beware of those kind of things. Like, you may actually end up causing allocations there. And so the right way of writing something that's equatable, to check whether two things are equal, is actually to use the equality compare of t.default and call the equals and get hashcode methods on those kind of things. And in fact, if you look at the code generated for things like anonymous types and so on, it actually uses equality compare of t. If you want to score a little bit extra points on your team and you're not using .NET Core yet, even consider storing that .default result into a static variable that you sort of use as a shared variable, because the call to default by itself also has some expense in it. That solved in .NET Core was pretty involved change at some level actually, but it's something to be aware of, that when you build those things that have deep equality, use equality compare of t. It's there to help you. Because in fact, this kind of code is plain dangerous as well, the previous code. Say this is not an enum, but it's a nullable enum or something, and you do just to get hashcode or dot equals or something, well, null reference exceptions are just around the corner, right? So doing it right, also gets you better performance in this kind of case, okay? Here's another example. This is an async lock. It's actually on the TPL blog, I believe. Stephen Tope actually has released this one a while ago as an example of how to build asynchronous synchronization primitives. This is a pretty common use case. If you like to use the using statement to have some kind of a block, like using some timer, or something that will measure how long this block takes, consider actually making your disposable object a struct. The C# compiler is smart enough not to call the dispose method through the interface, which will cause boxing. It will actually call the dispose method on the struct itself, knowing that that's the one that implements iDisposable. So it will avoid the boxing altogether there. So if you have a using statement, you will actually end up, calling, a non-virtual method here on the releaser struct, as opposed to making this thing a class or, whatever. So this is a small one, read only but with caution. Once you start using more structs, and be careful with structs, especially if they're mutable, don't do mutable structs. But here's a good example. I've seen cases where people say, oh, I see a field in a code review, right? And it's a field that's only touched in the constructor. Let me put a remark here to the developer. Please mark this thing as read-only. There are certain structs which are mutable. A good example is the enumerator struct of list of t. Now, this is just to drive home a point. The enumerator struct on list of t is a struct such that the for each loop doesn't cause any additional allocations. If you do a for each over list of t, it will see, oh, this thing implements the enumerator pattern. It has a get enumerator, it has a move next, it has a current, all that kind of stuff. I don't need to go through the IEnumerable interface, which will cause the allocation of an enumerator on the heap, which is an additional object on the heap that's not needed because we're just doing the enumeration in the context of a for each loop. So it's a struct for performance reasons, but it's also a mutable struct. It contains the cursor inside of it. So if you end up storing this thing in a read-only field, then updates will never be persisted to it. We'll just make it immutable, and the enumeration will just be stuck and not move forward. That's just to say mutable structs are evil, but sometimes when you do real low-level performance tuning kind of things, a mutable struct can be quite useful. In fact, all of the value tuples in C# 7.0 are mutable structs. So this plain advice of never use a mutable struct, well, never say never, right? There are certain cases where it does make sense, but then also be aware that certain things like marking things read-only all over the place may not actually preserve the correctness of your code. And that brings us to immutable data structures. Our system in Bing actually uses a lot of immutable data structures. Now, how many of you have actually played with system collections immutable? Like the immutable array type and all that kind of stuff. In fact, Roslyn, the .NET compiler source code, uses an awful lot of immutable design. And the beauty of immutable objects is, of course, that you can share them across multiple threads, and you don't have to have any price to pay for synchronization. Now, there's, of course, a flip side to the medal, because, well, if it's immutable and you want to change it, you need to create a copy. So you have to be careful on how you make those copies. The main thing here is actually to just raise awareness that there are immutable APIs already in existence that you can start using. Good example is the immutable collections types. If you, for example, have an array and it will be rarely changed, and you don't want to have any cost in acquiring locks on the array in order to read from it, so that if there's a concurrent update happening, you may get one cell updated and the other one not updated. If you want consistent reads, but you don't want to pay a price for synchronization, then you can actually start using immutable collections, where the mutation will create a new copy of the collection and just replace the reference from the old copy to the new copy. So those immutable collections are beautiful, and in fact, if you're in Visual Studio and you're just jamming on the keyboard, right, Roslyn is allocating new data structures for every keystroke. It's just creating new ASTs all the time in a memory-efficient way by trying to reuse as much of the existing data structures that it can. And that's the other beauty. Immutable collections lead to a lot of reuse. If you have, say, an immutable array and you just want to insert an element, well, we can actually split the array, and we can sort of create two segments of it and sort of create the illusion of you having a new consecutive array without copying the whole thing. We can just copy the head of it all the way to your mutation and then just point to the remaining tail of an existing array, so we can actually share all of that stuff in memory. And so immutable collections can help you to actually get rid of some expensive synchronizations. And so a good example of that is in our service, we have a lot of configuration that barely ever changes, okay? A dictionary of string to value, typical kind of thing. A lot of things can be optimized with dictionary of string to value. If they never need to be updated, well, don't make them into a concurrent collection, for example, because then you have a huge amount of, locks sitting underneath you that will be there in case there's a lot of writes happening on the thing. It's a read-only collection, for heaven's sake. Nobody's going to write to it. So then don't use a concurrent collection just because once on a day there may be an update to that collection. Like, use something else. Like, know the frequency at which reads are happening, writes are happening. If like 99% of the time it's reads, then optimize for the reads and don't slam in like some concurrent data structure when there is no concurrency to be expected on the write path, for example. So I'll give you an example of that. Here's something that happened a couple of months ago. Let me just take a quick look at time here. Yeah, I still have 5 minutes. I will be just in time. So this is an example where we had a configuration manager. The configuration manager would reload changes dynamically from some underlying source. It's an abstraction over a configuration system. In our case, it would listen to an event handler in Service Fabric saying somebody has deployed a config update. The code keeps running. We get a notification the config has changed. You can refresh the config and adapt your service to just, while it's running, pick up the new config, like beautiful system. So in this case, this configuration manager was encapsulating all of this kind of stuff. And there was a lot of frequent accesses to get the latest configuration settings. Now, there's already something you have to think about there. If you have config updates, how quick do you want them to be seen? Are you going to say nanoseconds? Are you going to say milliseconds? Are you going to say seconds? Well, in a lot of cases, the limiting factor is the human being able to hit the button. It's maybe because the system is in a crisis, so you want to be it as soon as possible to be picked up. But nanoseconds are not going to make the difference between the human, getting his coffee first and then saying, let me fix the system over here. So you can actually allow a couple of milliseconds to elapse before the config gets picked up. And so what was happening here is that the person writing the configuration manager had already done a lot of reading and said wow, look, we can use this reader-writer lock, because reads are going to be frequent, writes are going to be infrequent, and so the cost of reading should be less than the cost of writing, blah blah blah. And so he or she actually used the reader-writer lock around a regular dictionary. It's already kind of better than using a concurrent dictionary. It's one step up from that, because concurrent dictionary is very expensive in case it's ideal if you have a lot of concurrent writes. But if you don't have a lot of concurrent accesses to it, there's no point. So it's kind of better here, but then doing some performance analysis on this thing, the person concluded that doing a regular lock as opposed to a reader-writer lock was actually faster. Well, a reader-writer lock is there to assume that at some points there will be writes, and we sort of want to amortize the cost for all the reads and so on. But there will still be writes at some point, and there's a lot of bookkeeping to happen, whether the lock has to be upgraded, from shared and all that kind of stuff. So there's bookkeeping happening in there. And so we looked at that thing and we said, well, why do we need this? We already have a field which contains a dictionary, and every single read is going to read that field and then go into that dictionary. So when a config change happens, just prepare a new dictionary. It's a dictionary of 20 bytes. Well, not 20, 100 bytes or something, very small dictionary. Why try to protect against mutation inside a single shared dictionary if you can just swap out the dictionary for another one? So we just said, well, let's just change it like this. We have our dictionary. It's no longer a read-only field. And when the config change lands, we'll just create a new dictionary, take our merry time outside any kind of locks to prepare the new dictionary reflecting the configuration, and we'll just swap it into the field over there using an interlocked operation, which will also cause flushes and those kind of things. And so, very simple thing. The most naive kind of solution. Okay, there's some interlocked stuff here, but whatever. But as opposed to putting a lock around all of the single reads into a dictionary, that will be basically a publication pattern. You prepare it and then you share it with the world, and you never mutate after you share it. Very common pattern. Instead of doing that, let's just substitute the dictionary. Okay, so that's what we did over there. Very simple trick. Got us a long, long way actually. Now to wrap up, I'll just do key takeaways. Well, yeah, okay. Well, actually, let's just do the key takeaways, on this one, and we'll end over here. One interesting thing, this talk is something I've been giving in a couple of presentations in different conferences, just like my C# internals talk yesterday. If you actually look online, I think there may be already one conference that has this talk posted, and it's in a different order. I sort of tried to mingle the order so that, if I don't get to the end here, in another conference, the things that were at the end were at the front, so you can sort of get all of the stuff anyway. So the key takeaway of this thing is, okay, we have a configuration manager, we abstracted over it, we created a beautiful iConfiguration abstraction or iLogger abstraction, but it sort of contains a lot of cost inside of it, because what's really happening is that when Service Fabric tells us the configuration has changed, it just gives us a new config object. So if we would just do it naive, without some platform abstractions, because at some point we may move to a different platform, we would just be storing that config object in a field and just reading from it all over the place. Now, this abstraction actually caused us to introduce some additional kind of locking to copy things out of that new configuration object into our own object model, and then acquire a cost in doing so. So there's some cost to abstraction. You may want to have that abstraction in place. We decided to keep the abstraction, but be a little bit wary about all those little abstractions that you put on top of things, the iCounter, the iLogger, the iConfiguration. If you build those kind of wrappers, make them efficient, because those are going to be sitting on the critical path everywhere. For every single request, you may be going through those little abstractions, which are there because maybe in 5 years, when your product is irrelevant anyway, but you were sort of thinking in 5 years, this thing will have to move to a different hosting infrastructure, and we want to be ready for that. Well, believe me, at the point you need to move to another hosting infrastructure, it's likely not going to be the worst of your concerns. You'll have a lot of other things to look at. And so this little configuration utilities and so on, think twice, think carefully about them, okay? So with that, I'm at the end of my talk. If you have any questions, follow up and so on, please feel free to come to me. I'll be around at the conference for the rest of today and tomorrow, actually. And well, thank you for coming, and please come to me with any questions, okay? Thank you.